So today's lecture, I will give a brief introduction to variational quantum algorithms, but most of the time, I will focus on variational quantum eigensolver, namely VQE, because it is a very good template to demonstrate how problems are formulated and mapped onto quantum computers. And it explains the paradigm of hybrid computing with classical computers and quantum computers. So let's dive into today's like different sections. I have 4 sections, and after this, I will demonstrate a very small program to see the polystrings and to run a small VQE program. And I have, as I mentioned, I have uploaded the codes and the lecture notes onto the GitHub repo, so you can download that now for your reference, okay? So the first section will be electronic structure problem, then first, second quantization, then the fermionic operator to qubit mapping, and in the end, I will give a very quick recap and introduce the overall workflow of VQE. Okay, so let's begin. It starts from a very important problem, the electronic structure problem. For example, I have a hydrogen molecule. I would like to describe this quantum system. Then I can use time-dependent Schrödinger equation to describe the system. And we can see here that the psi represents the wave function, little r represents electrons, capital R's are the locations of the nuclei, and T, of course, is the time. So this is time-dependent Schrödinger equation. It's applicable when the system is isolated and non-relativistic. And when the Hamiltonian is time-independent, namely the Hamiltonian is not changing with time, the solution is a linear combination of these states. So Ck represents the coefficients, and phi k are the possible states, and Ek are the corresponding energy. And the equation is now transformed into a time-independent Schrödinger's equation. Looks like this. If you are familiar with linear algebra 101, you can see that it is in the exact form of like Ax equals to lambda x. Well, Ek are the eigenvalues and psi k are the eigenvectors. And this equation is actually very difficult to solve because we have the curse of dimensionality. So for the simplest example of the hydrogen molecule, the psi, the wave function, contains the the positions of 4 particles, right? If you are in a 3D space, which means that the wave function has 12 degree of freedom. If you try to solve the problem with numeric ways, you example 10 points on 1 dimension, then the total number of points would be 10 to the 12, like a trillion points, just for a very simple problem. So it's hard to solve. And when coming to more practical applications, for example, you want to develop drugs or drug discovery, you're dealing with proteins, the dimension would be like 100,000 for the wave function. If you still try to use numeric ways to do that, you are facing a number of data points of about 10 to the 100,000. It's more than the number of atoms in the universe. So here we are facing the problems of very high dimensionality. Therefore, the very first thing we want to do is to reduce the problem size to make it feasible to eliminate or omit everything that can be ignored or approximated. So the very first thing we talk about is the Born-Oppenheimer approximation. This approximation is based on the fact that the mass of the nuclei is way over the mass of the electrons. So when I have a system of nuclei and electrons, I can fix, like temporarily fix the location of the nuclei and just consider the motion of the electrons. So we can see that, again, the time-independent Hamiltonian Schrödinger equation, the Hamiltonian is composed of 5 terms. Out of the 5 terms, 2 of them are not related to electrons. So they are only the numbers about the nuclei, so they can be treated as offset. The other 3 terms, they have something to do with electrons, and we gather them together to form a new Hamiltonian, namely the Hamiltonian for the electron. It is a function of the locations for the electrons given the locations of the nuclei. So the locations of nuclei are fixed right now, like temporarily. And to be more specific, TE represents the kinetic energy, VNE represents the Coulomb potential between the nuclei and the electron. ZK, it's like obvious that is the number of charges on the nuclei. And VEE represents the interaction between electrons. It's a Coulomb potential. It is in a very a simple form because we use the atoms unit that the mass of the electrons equals to h bar equals to the charge equals to 1, so that we can have this clean form of expression. Okay, so we discard these 2 terms because they are treated as offset, and now we have a new Schrödinger equation. And to solve this equation is the electronic structure problem. It is basically what quantum chemistry is about, and it is the most important and hardest problem to solve in quantum chemistry, because it tells us the properties of a molecule. Say you have a molecule of different shape, and the horizontal axis is the reaction stage. The vertical axis is the energy. You might observe curves like this, right? So this electronic structure problem will allow you to calculate the energy at this local minima. And by doing that, you can derive the rate of reaction. So it is really important in the field of quantum chemistry. Okay, so our target now is clear, just to solve this Schrödinger equation. And the very first thing we do is the first or second quantization. Because if you think about orbitals in the electron orbitals in atoms, you have many energy levels, but for current quantum computers, most of them have just 2 levels, right? Qubit can either be like 0 or 1. It does not usually have access to higher energy states. So we need to map multiple orbits onto very limited 2-stage quantum computers we have, because like Richard Feynman pointed out that the most efficient way to simulate a quantum system is to use a quantum computer, right? And there is another approximation we will make during the process. That is the 1 electron picture, or the mean field approximation. So basically, we define some of the molecular orbitals and treat electrons in the mean field. So to give a more intuitive example, for example, I have, let me think about an analogy. So I have a fish, and it's swimming in the pool. You know that it feels the force of attraction and repulsion from the water molecules, right? But when you calculate how it moves, you do not encounter all these water molecules. You just encounter the resistance, the gravity, stuff like that. So you can think about electrons in an ocean of other electrons. So in this way, the overall wave function of electrons can be separate, can be divided into the product of single electrons wave function. But we're not using equals here because electrons are fermions. They have to obey the anti-symmetric rule, which means that if you change or if you swap two electrons, the wave function should have a minus sign in front of it. So it cannot be the exact product, but in a similar way, because now we ignore the correlation between the electrons. So for example, I have here STO3G basis for hydrogen molecules. It can be divided into 3 orbitals, 3 bases. So we can use these bases to represent the state of the single electron, like they are not interacting with others. I see a chat box. Is there anything? Just a moment. That in order to get a reaction rate, there are a lot of more needed than just solving electrons. For example, transition state search, solvent effects. Well, thank you so much for the supplementary comments. Yeah. So if you have any questions or confusions or disagreement, you can just point out in the chat box so that everyone can see and learn from it. Okay, cool. Thanks for that. Okay, so we cannot use the direct products of single electrons wave function as the overall wave function, but we can use Slater determinants as basis for the wave function. So the Slater determinants looks like this. This is one of the bases. Let's say I have n electrons and n orbits. And then the element inside this matrix are phi I x j. It will represent whether that specific electron is on that specific orbital. And xj contains the information of the spatial location and the spin direction. And we add a term of a square root of factorial n just to normalize this wave function. So let's take a look at the 2 electron example. So I have 2 electrons. I have orbitals I and orbitals j. The wave function, the Slater determinants look like this. And when you expand it, you will have like phi x1, phi j x2 minus phi x2, phi j x1. Clearly, it satisfies the anti-symmetry rule because phi j x1 x2 equals to minus phi psi j I x2 x1. So another interesting thing we need to notice is like if x1 equals to x2, which means that you have 2 electrons on the same orbital, the Slater determinant will give you a 0 for the wave function, which means it's not allowed. So that's basically the reflection of Pauli exclusion principles in the Slater determinants. So we can see that Slater determinants works with the anti-symmetric rule and the Pauli exclusion principles. So it is a perfect or it is a good set of bases. So therefore, the overall wave function of the electrons can be written as linear combination of these bases. And here we introduce a fork or occupation space where we use this vector to indicate whether the electron is on that orbital or not. And here NO represents the number of orbitals. So in the 2 electron case, it is something look like this. Like you have 2 electrons, I and J, and you just enumerate all the possibilities. They have the coefficients, and you just get a weighted sum of them. And then let's talk about the first quantization. We just learned that the overall wave function can be written in a form of linear combination of these bases, and the bases satisfy antisymmetric rules. So when you have a Hamiltonian acting on the wave function, it's a linear combination of Hamiltonian acting on that basis. Since the bases are complete and orthogonal, what you're doing is simply changing the coefficients. It's like I'm moving a dot from here to here. I'm just changing the coordinates, like of the, I'm just changing the number of x, y of them, right? So here, the antisymmetry is enforced in the wave function, or to be more specific, it is informed in the basis wave function. And then we introduce the second quantization. Remember the fork space we just talked about, where n represents either electron is on that orbital. Here we introduce the creation operator. Basically what it does is, like, if there is no electron on that orbital, after this operator is applied, there will be one there. So this is called creation. And we have the annihilation operator as well. So it will remove the electron from that orbital. And let me explain why there is a delta Ni0 here, because if Ni equals to 0, there is no electron there. So the operation is legal. It is possible. If Ni equals to 1, which means there is already one electron on the orbital, you cannot add another electron on that orbital. And the term here exists to make sure that the antisymmetry is maintained or satisfied. So in second quantization, the antisymmetry is enforced with the properties of operators. So basically, this is the one of the difference between first quantization and the second quantization. And so before, so I just described how the wave function is decomposed or projected onto this basis. Then I'm going to talk about how the Hamiltonian is projected onto the space spanned by phi I xi. So these are different orbitals. According to the Slater-Condon rules, we have these 2 sets of coefficients, and the Hamiltonian can be like written with these coefficients. If we look closely at the coefficients, we can notice that phi p, phi q, if you apply it on phi q, it just change, like, say this is an operator. If you apply it on phi q, you will get phi p. So it is very similar to, or it is the same as applying an annihilation on orbital q and the creation on orbital p. Therefore, we can just directly replace this operator with the creation and annihilation operator here. The coefficients are the same. And even though the HPQ and the PQRS are in this some kind of complicated integration form, they need to be computed on classical computers. That is, you have to do the integration by yourself to get these coefficients. So yeah, it is easy to calculate the coefficients, but it is hard to calculate how the quantum system evolves. Okay, so to this point, our Hamiltonian is in the form of fermionic operators. And now the final step is to map them onto the qubits, where we have only like zeros and ones, like high energy state and low energy state. And yes, just a reminder that the wave function, when we write them in the form of linear combination of this vector, a 0 on jth element means that the jth orbit is not occupied, while 1 on jth orbit means that the jth orbit is occupied. So when you have a creation operator, when you act on 0, it will give you 1. So AJ is actually look like this. And you can further transform, you can further use a Pauli matrix to represent this 2x2 matrix. But remember, we need to enforce anti-symmetry. So all the orbits, so I have NJ here, all the orbits before it should be applied with Z gates to enforce the anti-symmetry, because now the basis does not enforce anti-symmetry. We have to use operators to do that. So this is the idea of Jordan-Wenger mapping, JW encoding. We'll see this name later in the demonstration. So when you have the creation and the annihilation operator in the form of Pauli operators, when you substitute them here, you can get a Hamiltonian equals to the sum of some weight and a Pauli string. The Pauli string is made up of I, X, Y, Z times N. So a simple example would be Hamiltonian equals to, say, 0.1 times X, X, Y, Y plus 0.2 times I, Z, Z, etc., etc. So we transform the Hamiltonian of the problem into a weighted summation of Pauli strings, and this is how it's possible to map them onto quantum circuits. And then I'm going to introduce another way of the fermionic operator to qubit encoding. It's called parity encoding. In case some of you are not familiar with parity, parity basically measures the number of ones inside like a string or list. If there is like odd number of ones, then the parity is 1. If there is like even number of ones, the parity is 0. So if there is no electron on jth orbit, well, let's first define how parity encoding, what parity encoding is. So for parity encoding, we have N1 all the way to N number of orbits. So Nj is the parity of everything like from 1 to J before it. So it is the parity of the sum of the electrons before this orbit. So when jth orbit is not occupied, the parity should not change between J minus 1 and J. Therefore, you can only have 0, 0 or 1, 1 at position J minus 1 and J, right? And when you have an electron on that orbit, then the parity would be different from the previous qubit, So it can either be 1, 0 or 0, 1. Therefore, when I have a creation operator, it will change the state of 0, 0 to 0, 1, because this is j minus 1, it is not affected. This is j, I have an electron here, therefore the parity changes. So the operator looks like this. The same story here, but we have a minus sign here, because remember, when we apply creation to this like a vector, we will have a term that is minus 1, 1, 2, j, minus 1, and k. So the parity automatically calculates this term, because if the parity is 0, it means that there are like even number of electrons there. So you just like minus 1 to the power of an even number, it is 1. And when the parity is 1, it means that there are like odd number of electrons on the orbitals we say before. So the minus 1 to the power of an odd number, you get minus 1. So we can transform this to polystrings like this. So we can see that it won't affect the numbers in orbits like before that, but it will affect the qubits after that. Why is that? Because you create an electron on jth qubit, which means that the parity changes on all the qubits after that. So you need to append X gate to each of the orbitals after jth orbital. And this is called parity mapping. So, I mean, either way, either it's JW or parity mapping or some other mapping, BK, the ultimate goal is to have the Hamiltonian written in this form, a weighted sum of polystrings. And then say I would like to calculate the lowest energy and the lowest energy state of a given system. Then I can just measure it with a wave function psi, just read it here, psi Hamiltonian psi, and in this way I can get the expectation value, and it is larger than the lowest energy. So, for example, even I start with some random states. Say I start from 0, 0, 0, 1, 0, 0, 1. I measure and obtain the expectation. It will give me an upper bound on the lowest energy. So our goal is to iteratively update this upper bound so that it can approximate the exact lowest energy. So the EQE, the task is to minimize this weighted sum. Okay, so the way to do that is to use a variational circuit, or you can call that ansatz, times the initial state. Sometimes it's 0, sometimes it's Hartree-Fock. We want to use this state to approach the state with the lowest energy. And we will talk about like how to do that later. Actually, it's not an easy task. So for quantum chemistry, they propose like unitary coupled cluster. It's actually derived from coupled cluster. So coupled cluster are like sigma n, Tn, and unitary just use E like A minus A dagger to make it a unitary matrix. So what does Tn look like? For T1, it means like single excitation. It's made up of a parameter, annihilation and creation operator. So annihilation means that the electron goes from here to here, and the double excitation basically does the same thing. It's just like two electrons are like excited to a higher energy state. And if we do some like transformations and totalization, we can map the unitary onto the quantum computers. The one important part is called totalization. It basically uses the approximation. You basically use the approximation to transform the exponentials to a form that can be mapped onto the quantum circuit. And K is an parameter. You can choose K equals to 1, 2, 3, etc. If it is larger, then the algorithmic error is lower, but it will introduce overhead on the circuit. And for most of the time, the UCCSD performs great with the molecules because it captures the essence of the electron correlations in the molecule. So we just finished the like several things. The first is from Hamiltonian to transforming into weighted polystrings. The second thing is to transform the psi into Fock space, and all of these is just to map the problem onto quantum computers. And then I will give here overview of the variational quantum eigensolvers. We just covered this part, and sets. Yeah, we didn't cover like how to measure these polystrings. It's actually very intuitive. So for example, you have a polystring that is x, like ix, xi. You just need to append rotation gates to the middle of the qubits and obtain the results, like obtain the expectation as usual. Here, mentioned in the graph is like grouping and measurement weighting. Basically, it's techniques to reduce the number of polystrings, because I will do a very short calculation to see that the problem of VQE is the overwhelming number of measurements required. And as for the parameterized circuits, we want this to approximate the lowest energy states. How to do that? Of course, you can use non-gradient based ways, or you can use gradient based optimizer. So the way to calculate gradient is stated here. It's called as parameter shift rule. So basically, I want to calculate the gradient of theta, and my expectation function looks like f theta and other parameters. The gradients would be f theta plus pi over 2 other parameters minus f theta minus pi over 2 other parameters. So it looks like linear approximation for gradient, but surprisingly, it is an exact gradient. But it introduces the problem of 2 more extra measurements. So to obtain the gradients for one parameter, you have to run the circuit like twice and compare the difference in the expectations. But we omit the back propagation calculation. The price is that we need to measure more. So I will give a very small example here. I have a small molecule, maybe 2 or 3 atoms. The number of parameters, say 100, and I have a perfect optimizer, so it will converge in 100 iterations, and I have perfect quantization method so that the polystring is 100, and for each circuit, I just run it 1,000 times. The total number of measurements is still like 2 to the power 9. We have two here because we need to use parameter shift rule to calculate the gradients. So the massive number of measurements comes from the massive number of polystrings, and usually the polystring scales with ON4, but with some grouping or like classical shadows techniques, you can further reduce this number to some ON squared or I'm not clear. I need to check that. But anyway, if you want to optimize the VQE algorithm, these 4 directions, like they are the sources for overhead. So you can always optimize the VQE from this perspective. Say you have a better ansatz with less parameters, or you have a fantastic optimizer that converges fast, or you have a better grouping algorithm with low overhead. You don't need to calculate the commutativity or stuff like that, or you have just a perfect quantum computer so that you don't need to run that many shots, because just to mention that the number of shots to obtain certain results is of error epsilon requires like 1 over epsilon squared, that much that many times of measurements. And that will be it, a very short introduction to variational quantum algorithms. And I know you have we have experts from quantum mechanics or quantum chemistry here. They might find this content very familiar with. Let me stop the share, and I will switch to a laptop to demonstrate the programs. Okay. Maybe we have a 1 minute or 2 like QA session. Does anyone have any questions for now? Hello? Anyone? Okay, if not, I'm going to.
Yeah, I have a naive question.
Yeah,
like,
sure.
For the gradient evaluation, is it on the classical or the quantum hardware?
It is on the quantum computer.
Oh, okay.
So like,
and then,
yeah,
but the optimization of the parameter, like the theta that you mentioned, is on the classical.
Yes, and there is much space for optimization. You can check the newest like ISCA paper, like EQC, to see how they deal with that. Okay.
Okay, thank you.
Yeah. Thanks for the question. I want to emphasize that for VQE, we do not need to use back propagation to calculate the gradients. We just need to measure, obtain the expectation, and that will give us the gradients. Yeah.
Hi. I have a question.
Sure.
I'm Kai Tao. So you mentioned a term called anti-symmetry several times in the talk. Can you please?
Yep.
I am interested in the symmetry stuff. Why is symmetry a good thing, or it is not a good thing, and why you're doing anti-symmetry?
It is not good or bad. It's actually principles of these particles. So as I just mentioned, you swap the electrons, and the wave function should have a minus sign there. There are some other cases when you swap the particles, the wave function is exactly the same. We call these particles as bosons, and when you have a minus sign there, we call them as fermions. So basically, they are like the properties of the particles. It's not like manually designed or designed by humans, you know. Yeah, it's like we have to obey the rule.
Okay, I thought the symmetry is in the coefficients, or.
I beg your pardon?
Okay, I thought never mind. So another question is, could you please go to the minimization function of the VQE?
Okay, 1 second. The minimization function of VQE, like
Yeah.
here, right? There's some lag here.
Yes. So we see that there's a broad zero and cat zero at the left side and the right hand side.
Yes.
And in the middle, you see the things you want to optimize, the theta thing.
Yeah.
So can you please explain this a little bit more? It's like 0 is the initial state, and then operations on the cat zeros, and then it's like from an initial state 0 to a new state. Is that right?
Can you repeat the question? I mean the last part of the question.
So you always assume that the initial state is the 0, right?
Yes. For this
and then,
equation, yes.
And then the initial state 0 will go through some quantum circuits that is parameterized by theta, and then you get a new state, right?
Yes, yes.
And that new state, like it's like a new initial state that will minimize some functions.
Yes, that will approach the lowest energy state.
Okay, so it sounds like you are generating a better initial state than the all zero state. Is that right?
You can claim that because variational quantum algorithm, one of the motivation is to use that for state preparation in quantum phase estimation. Because in quantum phase estimation, you need to prepare the state. And then they propose that you can use a variational circuits to prepare the state. And you mentioned that I start from 0 here, but of course I can start from other states. Say I can start from Hartree-Fock state, where I have a bunch of zeros and ones. So this initial state works with the UCCSD because it has some specific physical meaning.
Okay, I see. Okay, thank you.
Thank you for the question. Okay, so I will stop share and jump to the laptop. Maybe I should use a terminal. Okay, so you can try to follow me with 1 second. Is it too small? I think it's too small. Let me adjust that. I can use Visual Studio Code. Screen. Where is VS Code? Okay, here. So here, this is the installation hints. So if you want to run this, program on your own computer, you can check our code here, installation hints. The lecture notes, I mean, what I just showed is also uploaded. So when you go through the procedure, I tested many times by myself on different machines. It should work, okay? If it doesn't work, you can like send us emails to solve that. It should work. And say I just Python demo polystring. It will give me a list of weighted polystrings. And let's take a brief look at the code. So I'm using QuCS to do that, but actually QuCS does this through the PySCF. So that's why you see pipe install PySCF here. Let me zoom this. So the structure of the molecule is defined in this line. the position of the first hydrogen atom is 0, 0, 0. The position of the second hydrogen atom is 0, 0, and your parameter. The unit is angstrom, the basis is STO3G. As I mentioned in the lecture notes, we use molecular orbitals as basis in the 1 electron picture. And then we use the second quantization. Let me see, second quantization here, and use the parity mapper to map them onto the qubits. Therefore, we get something like this. So we can change the mapper. Say, I want to check this mapper to see if it performs. I save it, and run the code. We can see that it generates the polystrings as well, but we have many more terms. So we can see that there's indeed some difference in the fermionic operator to qubit mapping. And actually, the locality of these mapping methods are different. Also, if we take a look at these terms, like they are composed of only I and Z, which means you don't need to add extra rotation gate to perform the measurement. So even though I have like 10 polystrings, I just need to measure them once, right? I measure them once and I obtain the expectations and do the calculations like times the coefficient, stuff like that. So let me do a simple example here. Say I obtained, my Hamiltonian looks like this, and I obtained a distribution like 0, 1, 0, 1. So accidentally, all my outputs are 0, 1, 0, 1. So the expectation for the first term would be 1, for the second term would be 1, for the third term would be, oh, it's not a good example. Let me change a little bit. 0, 1, 1, 1. So the first term, it would be -1. For the second term is 1. For the third term, it's -1. Then these are the expectations I calculated from the output distribution. Say I run it 124 shots, and all of the outputs are 0, 1, 1, 1. Then I can calculate the energy of this Hamiltonian just by summing them up. Okay, so yeah, and then we can try to see how a VQE algorithm work. I thought I have it here, but it's not here. Never mind. Wait for a moment. Anyway. I cannot deactivate.
But you just need to conduct deactivate, like you don't need the environment name. Just conduct deactivate, like it will go.
Oh, I see.
Help you to go to the base.
Thank you for the demo. Sorry, I delete all these demo environment because I want to test if the installation hints work on like brand new computers, you know. Give me some time. Well, we can check the code first. This is the Torch Quantum provided by Harry Wang. He's also here. He's the author of the Torch Quantum. We can check the examples. Simple VQE.
You're not sharing the. Jinglei, you're not sharing the whole.
Okay, I see. This is stupid. Sorry, I apologize for that. share screen. I just share the desktop. It's easier. So this is the simple VQE is in torch quantum examples. Simple VQE. We can see that the variational quantum, the variational circuits is in this part, and it takes the Hamiltonian strings from some text here. So this is the name, the mapping, name BK, and number of qubits you need. These are Hamiltonian strings. So the problem take this text as input, and it will use optimizer to run the VQE algorithm. I would like to demonstrate that here. So let me see. Yeah, basically, well, you can also check this program to see how it works, and you can try to replace these, like U3 layers and CU3 layers to your own ansatz, say hardware efficient ansatz, stuff like that. And the search for best architectures for ansatz is also a very popular solution direction right now. Well, in the meantime, does anyone have questions about these two small programs, like this demo polystring, the ways to calculate? Yeah.
Yeah, I have a question about the GitHub, like the source code. Why do we need torch there? Because I think you just mentioned that like we don't need any gradient, like the backpropagation, like in the VQE. So why do we need torch just for the? Oh, I did see the loss backward though, like.
Yes, Harry, can you explain your code?
Sure. Maybe I can add one point here. So for this torch quantum, we have two different support. One is to use the backpropagation to obtain the gradients, but we can also use parameter shift to obtain the gradients. So that's just the two ways of obtaining gradients. So we support both method, and here in this demo we use backpropagation because that's faster. So, but
Okay.
the partnership is also supported. Yeah. Actually, in the simple and there is another folder called VQE. So in that one we have the partnership, and also like the partnership on-chip training. In that folder, we also have the partnership code example.
Here?
Yeah. Not this, the partnership, the another folder. Yeah,
Partnership on-chip training.
Okay.
Yeah. So, yeah.
So should maybe we should mention that backward or backpropagation is not possible for real machines. It's only plausible on simulators, right?
Yes.
Oh, okay. Yeah. Like also question about the gradient measurement, since you mentioned that the gradient is computed on the quantum hardware. Is it like, since it's on the quantum hardware, is it just like kind of like you do multiple shots of measurement to have a estimation of the gradient? Because like it may, like it's a probabilistic distribution. Like
yes. So I mentioned that the gradient is the difference between two expectations, right? To obtain one expectation, you need to run the circuit many times.
Yeah, okay, I see. Thanks.
Okay, so now we have torch quantum here, and example simple. I remember that we can direct run it with default settings. Yes, it's running. So we can see the decrease of the expectations, like at different iterations. My computer is just too slow. Okay, you can see here that it supports backpropagation. So we can see the decrease of the energy. But in real world, when you run it on like quantum computers or noisy simulators, because it has noise, it's not guaranteed that after some epoch, the energy is reduced. And when you have too many qubits, you will run into the problem of barren-prone 2 as well. Okay, so this finished the lecture of today. You can always download the code from our GitHub repo. And if you are interested in quantum computing, you can always check Torch Quantum to see if it can implement your application. Okay, and that's it. I'm going to stop share. And thanks for listening.
So does anyone has any questions for today's talk? Oh, I saw a hands up. So yeah, Fen Qian, do you have any question?
Oh no, I just say it's good. But I actually have one more question. So when you do the like optimize the parameter for the VQE, and do you have any specific optimizer you use, or have you ever compared like different optimizer to different molecule and see is there any relation between that?
I would say it would be a very interesting work. I see comparisons between optimizers, but they seem to be on similar task. You can try to see if different optimizations have different performance on different molecules. Yeah, maybe you can send me an email. I can email you the paper about optimizers. There are some like prior work there.
Sure. Because like previously, I was also working on VQE stuff, and the one thing I was pretty curious is like, so for different basis set, you basically just split the molecule into like different basis set. Basically, you can understand like it's like accuracy. But I think I remember one paper mentioned different optimizer to different basis set, they get certain relation. So like some basis set is good for certain optimizer. So it's
Are
like,
you talking about basis set or like the mapping algorithm?
a basis
Like
set, not a
like STO3G, 301G, these different basis set?
yeah, that kind of basis set.
Oh, that's interesting. Yeah, we can. Yeah, it's a very interesting topic.
Okay, I see. Cool. I will send you an email and please give me the paper information.
Okay.
Thank you.
Thank you. Thank you.
Okay, if there are no further questions, we will end this talk today and hope to see you next Thursday. Thank you so much for attending our lecture series.
Thank you, guys. Thank you.
Thank you very much.